Okay, welcome back. Now, in the previous video, we learned about the microcanonical ensemble in our statistical mechanical treatment of an isolated system. That is to say, a system that has adiabatic, impermeable, and rigid boundaries. So now we want to release some of those constraints, and the first thing we're going to look at is the canonical ensemble, where we're going to allow the system to exchange energy with the surroundings through heat. So we're going to allow the system to have diathermal boundaries, but we're going to keep the rigid and the impermeable boundaries in this section. So the basic approach is like this. We're going to create a super system which contains two systems. One is our system that we're interested in, and the other one is a reservoir, the surroundings. And the super system, which I've delineated here with the thick black line, is an isolated system. So it has rigid, adiabatic, and impermeable boundaries. But inside this isolated system, we have the system, inside the isolated supersystem, we have the system which has diathermal, but also rigid and impermeable boundaries. So we allow the system to interact with the surroundings, which I'm going to call the reservoir. And the reservoir generally is much larger than the system. And the diathermal boundaries allow energy to flow from the reservoir into the system and back. Okay. Now, the supersystem has a total number of particles, molecules, or atoms, which is just the sum of the number that's in the reservoir plus the number that's in the system. Similarly, the volume of the supersystem is the volume of the reservoir plus the volume of the system. And we know that the supersystem is isolated and it has a constant energy, which we'll call E sub T. Okay, so that's what we know about our supersystem and the two systems that are in it, the system of interest and the reservoir. Now, the Hamiltonian that describes the supersystem consists of three terms, or can be split up into three terms. One term is the Hamiltonian that describes the interaction among the particles in the reservoir. The second term is the Hamiltonian that describes the interaction among the particles in the system. And then the last term describes the interaction between the particles in the system and the reservoir. So this term, this H potential energy term, this is a potential energy term that allows the energy to exchange, to flow from the system into the surroundings and back. That's essential for us to reach thermal equilibrium. But the important thing to keep in mind is that the system is very large and the surroundings is very large, and the size of this interaction is actually a very small contribution to the total Hamiltonian of the system. And in fact, actually, the potential energy of interaction is very small compared to the Hamiltonian of the reservoir or the Hamiltonian of the system. So even though this is essential for getting us to thermal equilibrium, the energy contribution from this term is small compared to the energy of the system and the energy of the reservoir just by themselves. So we can then approximate the total energy as just the sum of the energy of the system plus the energy of the reservoir, which I've written here. Now I'm going to use indices, gamma for the index for the microstate of the system in its corresponding phase space, and gamma prime as the microstate of the surroundings in its corresponding phase space. So there are two phase spaces here, the phase space of the system and the phase space of the surroundings. And of course, then there's also a phase space of the combined system and surroundings, which is the phase space of the supersystem. Okay? Now, in the canonical ensemble approach, the system can gain or lose energy to the reservoir because of these diathermal boundaries. Okay? Now, when the system energy changes, it's going to move from one constant energy hypersurface in its phase space to another constant energy surface in its phase space. So remember, in the microcanonical ensemble, the energy was constant, so the system can only be on one constant energy hypersurface. But in the canonical ensemble, the system can change energy, so it can move between these different hypersurfaces. So you think about this as kind of like a multi-dimensional, excuse me, a multi-dimensional onion. So you have all these different layers, and the system, when it changes energy, moves between these different layers. Now, each layer then will have some subensemble of microstates, which is counted, just as we did in the previous video, knowing E, V, and N for the system. Now, the microstates that are on the same constant energy hypersurface are all going to be equally probable. But microstates that are on different constant energy hypersurfaces will have different probabilities. The canonical ensemble, then, will be the complete set of microstates from all that's on all of these constant energy hypersurfaces, and that is the ensemble that we're going to be working with in this situation here. Now, the question then becomes, what's the probability that the system is on one of these constant energy hypersurfaces? All right, and that's what we're going to look at next. Now, if we knew that the system was in a specific microstate in its phase space, so we knew the value of gamma, and we knew that the surroundings were in a specific value in microstate in its phase space, so we knew gamma prime, then that would mean that the number of microstates we needed to describe that situation where we know these values of the indices is just simply the product of the number of microstates that we know the system has access to times the number of microstates that the reservoir has access to. But if we know these values, then this is 1 and this is 1, because we know exactly which microstate they're both in. So that means that the number of microstates for the total, the supersystem, is just 1. Okay, that's kind of a silly example here, but I just want to be clear about how this works. Now, if I only know that the system has an energy E and the surroundings have corresponding energy E prime, then we don't know which microstate they're on. That we know that the system is in one particular constant energy hypersurface, and a corresponding, the reservoir is also in some corresponding constant energy hypersurface. So, but we don't know which microstate on those constant energy hypersurfaces. So then we would have to say that the total number of microstates accessible to the supersystem is the product of the number of possible microstates for the system times the number of possible microstates for the reservoir, consistent with the energy of the system and the energy of the reservoir. Okay, so there's two constant energy surfaces in the system phase space and the reservoir phase space. We count the microstates in both of those spaces, and we multiply those two numbers together, and that's the total number of microstates for the supersystem. Now, because the energy of the reservoir is also dependent upon the energy of the total energy and the energy of the system, we can actually then rewrite this in terms of the energy of the system as this number of microstates for the system times the number of microstates for the reservoir, but now it's a function of the energy of the system here. Now, if I didn't know the energy of the system nor the energy of the reservoir, then I'd have to include all possible microstates that were accessible of the system and the reservoir. So what I would have to do is I'd have to sum over the product. This is the number for if I knew the energy was on a given constant energy hypersurface. But if I didn't know, I'd have to sum over all possible values of energy that the system can have, and that would be the total number of microstates that the system would have. So this would be the total number of microstates that is consistent with the total energy in our system if we didn't know, what the energy of the system or the reservoir was. All right. Now, the probability then that the system has a very specific energy, we'll call this E sub I, then would be the number of states that it's associated with the system having a specific energy, which would be this here, divided by the number of states where we didn't know what the energy was, which would be this here. So if we took this quantity and divided it by this, that would give us the probability that we have the system in a state with a constant energy EI. okay? And we can write this in terms of the energy of the system and the reservoir, but of course, since the total energy has to be constant, then we can write that in terms of just the energy of the system in this expression here. So this is the probability that the system is on the ith constant energy hypersphere, so hypersurface. So this is the specific, saying that it has a specific energy E sub I. Now the probability that the system has this specific energy is actually a very, very sharply peaked function, because the fact that the number of molecules is on the order of 10 to the 20 or 10 to the 23rd. And the reason you can see that is if you remember that the number of states is proportional to the energy raised to the power of approximately 3n. So that means that any tiny shift of energy, say from the reservoir to the system, would lead to a massive increase in the number of states for the system and a massive decrease in the number of states for the reservoir, and vice versa if you did it the other way. So that means that we're going to have this very sharply peaked probability function here. And we can look at this function here and learn something about the system when it is in this most probable state. So when we're going to say that if we find that most probable state, we can just take the derivative of this with respect to the energy. And if I take this expression here and I take the derivative with respect to energy and set it equal to 0, then this energy is the energy of the most probable energy of the system. And that is what we call the mode in this distribution. So if I want to take this expression here, I can rearrange this expression into this form here. So where I make note that the energy of the mode for the reservoir is just related to the mode of the system, since they have to add up to the total energy, and then the change have to be consistent here. And so we can then write down that expression here and write it in terms of everything with regard to the reservoir on this side, everything with regard to the system on this side here. And looking at this, you see that we have the partial derivative of the number of states divided by the number of states here and here. And if we recall our rules for the derivatives involving logs, we can rearrange these or condense this down to just the derivative of the log of the number of states with respect to the energy, so for the reservoir and for the system. And then we're going to define this derivative as a quantity called beta, where beta is the derivative of the partial derivative of the log of the number of states at a given energy with respect to the energy. And this beta, as we see in this example, at the maximum, the beta for the reservoir has to be equal to the beta for the system. And when we look at this, we see that the log of the number of states is just the entropy from Boltzmann's law, which we saw in the first chapter from Boltzmann's equation. And this term we learned from thermodynamics is just the temperature. So that means that this beta term is just 1 over kBT. And kB is just the Boltzmann constant, which is a constant. And so that means that this result here implies that when we were in the most probable microstates, that the temperature of the reservoir is equal to the temperature of the system. Okay, so we see that we come to thermal equilibrium when we reach the point where we reach this maximum in the probability. We are at thermal equilibrium. And that's what we see in this derivation. All right, now let's take a look at coming up with what's called the canonical ensemble partition function. And this will be the function that we'll use for deriving all of the thermodynamic quantities in this particular situation. So, question is, what's the probability that the system is in the gammath microstate? So we've already looked at the question, which was what's the probability that it's in the ith constant energy hypersurface, but what's the probability that it's in one specific microstate? Okay, so this is a much stronger probability in the sense that we want to know it's in one specific microstate. So if we know it's in a given microstate gamma, then that means that the only thing we don't know is what are the microstates of the reservoir. We know that the reservoir is constrained to be an energy of the total energy minus the energy that's associated with this gammath microstate, but we have all these possible microstates that's on some constant energy hypersurface in the reservoir's phase space that we have to count. So we know there's only one state for the system, but we have all these microstates for the reservoir. So the probability that the system is in the gamma microstate is just all the number of states that the reservoir can have divided by the total number of states that the supersystem can have, which we had before. Now be careful. This is the probability that the system is in the gamma microstate. That's not the same as saying the system is in one of the microstates that's on a constant energy surface. Okay, they're different here, but they're related, obviously, and we'll come to that. So if we take this expression here and we take the natural logarithm of both sides of this, then that becomes this, remembering our rules for logarithms here. And so we have this term here, which is essentially just a constant because the number of microstates is not going to change if the total energy is constant. And notice that I've dropped the indication of the energy, the number of moles, or the number of atoms or molecules, and the volumes in all of these last couple slides because they're all constant throughout this. So just to make the math equations look a little simpler. Now, if I take this expression here, I can see that these are really just logs of the number of microstates, with Boltzmann's equation just becomes 1 over kb times the entropy of the reservoir as a function of this energy minus the entropy of the supersystem. So given this expression here, I can start to simplify and calculate what this probability function is in a more analytical expression here. So what we first do is we assume that the reservoir is much larger than the system, and that's something we've talked about earlier. And that allows us to take this term right here and say it's going to be already pretty close to its equilibrium value, but if the energy of the system deviates, then it's going to deviate away from its equilibrium value. So what we're going to do is we're going to write down the entropy of the reservoir as a Taylor series expansion about its equilibrium entropy, and then we're going to have these extra terms here, and we're only going to go out to the first term here because the difference here between the energy of the reservoir as the system moves away from its equilibrium energy is going to be so small that we can ignore these higher order terms. This term right here we recognize as the derivative of the entropy with respect to energy is just 1 over the temperature. So that term becomes this term right here. So we see now it's just the energy of the entropy of the reservoir plus the energy of the reservoir minus the energy of the reservoir. So in other words, this is the equilibrium energy of the reservoir, but plus this deviation away from that equilibrium. So this is the deviation away from that equilibrium here, and that's divided by the temperature there. Now, let's do some more simplifications on this. Since this E prime, the energy of the reservoir, is got to be constrained by the total energy of the supersystem, then we know the total energy of the supersystem also has to be equal to whatever the equilibrium energies are of the system and the reservoir here. So these are the equilibrium energies of the system and reservoir. That also has to be equal to the total energy. So I'm going to substitute those in for ET, E sub t, and that gives me this expression. And then rearranging this, I get that E prime minus U reservoir. So in other words, the deviation of the reservoir from the equilibrium energy is equal to the equilibrium energy of the system minus E gamma. Okay, so what I've done is I'm trying to rewrite this so it's not in terms of the reservoir parameters, but in terms of parameters that describe the system. So now I can take also the fact that entropy is an extensive property. So entropy of the supersystem has to be the entropy of the system plus the entropy of the reservoir. I can rearrange that to give me the entropy of the reservoir is equal to the entropy of the supersystem minus the entropy of the system. So that allows me to substitute into there, and this allows me to substitute into there, and now the entropy of the reservoir becomes written this way. So now it's written entirely in terms of parameters associated with the system or the supersystem. So here's the supersystem entropy, here's the system entropy, here's the energy of the system, and here's the microstate energy of the system. So this is the equilibrium energy of the system, and divided by temperature. So if I take this and I substitute it back into my original expression from the previous slide, which is reproduced here. Then I plug this into this expression. You can see that the total entropy is now going to subtract off here, and that's going to disappear. And we're just going to have left this term, which looks like this when I rearrange it. And we recognize the equilibrium energy of the system minus T times the equilibrium entropy of the system, which is the Helmholtz energy of the system divided by kBT minus the energy of the microstate divided by kBT. So now we've done this great simplification where I'll take it to the next, okay, so I'll rewrite it here, sorry, as the entropy, the Helmholtz energy over kBT, so we'll just put it all together in one term. And I'll then write it over here in this form, and now I just take the exponentiate both sides, and this gives me that the probability of the system being in the gamma microstate is going to be equal to this term, the energy associated here, divided by the energy associated with the Helmholtz energy. So these two exponentiated energies divided by kBT. Now, we require probabilities to be normalized, so they must sum to 1. So if I insist that the sum over all these possible gamma values gives me 1, then that rearranges to tell me that this term, this exponential of the Helmholtz energy divided by kBT, has got to be equal to the sum over all microstates that's accessible of this exponential. And we define that term here as what's called the canonical ensemble partition function. And what we see right away is that that is equal to the exponentiated minus f over kBT. So if I take the log of both sides, I see that from this function, I can derive the Helmholtz energy term. So now we find that this function here contains information about the thermodynamic properties. So here we have the microscopic picture, which is the energy of the different microstates that the system has available to it. And from that summation at the microscopic picture, we predict the macroscopic Helmholtz energy. And we can do this with other types of energies and other thermodynamic properties, all derived from this one function, which we call in statistical mechanics the partition function. In this case, the canonical ensemble partition function. So given this here, I'll rewrite it over here like this. This is the probability that the system is in the gamma microstate, in a very specific microstate in its phase space. Now, we also know that when a system is in a gamma microstate, there's also a constant energy hypersurface that gamma is associated with. So if I wanted to know the probability that the system is in a given hypersurface, then I could just simply multiply, use this expression up here and multiply it times the number of microstates on that microsurface, on that hypersurface, sorry, and that would give me the probability that the system is in a system with that fixed energy here. So I can just take this expression here and I can modify it by just multiplying it times the number of microstates that have the same energy, and that gives me the probability that the system has that energy E sub I. And then similarly, we can use that same kind of logic to rewrite the canonical ensemble partition function in this form here, where we again use the number of microstates on the hypersurface of constant energy E sub I. And finally, if we wanted to go into the classical limit where we replace these summations with integrals, then it would look like this, where this function right here is what's called the density of states for our system. Now let's just take one last example here. Let's say we have our partition function. We know from the partition function we can calculate the Helmholtz energy. What about the internal energy for the system? We know that that's just a weighted sum of the energy for every microstate times the probability of that microstate. And with our partition function on this previous slide here, we can write that in this form here, where we multiply E times the partition function for that microstate times the probability using the partition function here. And we can rearrange this, and I'm going to do something that seems like a little odd here, but trust me, it'll be useful here. I'm going to take the partition function and factor it out of the sum side because it doesn't depend on the gammas. And I'm going to multiply times minus kbt and divide by minus kbt here to make this term in red. And then what I'm going to do is show you that if I had the partition function and I took the derivative with respect to 1 over t, that it actually gives me exactly the same function here, which means I can replace this in my expression for the internal energy with just that. So I can write down that u is equal to minus kbt over the partition function times the derivative of the partition function with respect to 1 over t. And now I can go ahead and slide these partition functions over. So now I have dq over q times 1 over the derivative, partial derivative with respect to 1 over t. And that, I know from the calculus with derivatives of logarithms, is just simply minus, and now it's just the partial derivative of ln of q here. So that simplifies this to this term here. And then we also know that the derivative of 1 over t is just minus dt over t squared. And finally, we get our result here, which is an expression where we can get the internal energy, the equilibrium energy from a system that is from a canonical ensemble where it has a diathermal boundary with surroundings with rigid and impermeable boundaries, from this expression here where this is our microscopic picture. This is the canonical ensemble partition function. And from that, we can extract the internal energy. Okay, so that's it for this section. In the next section, we'll look at the simple case where we have non-interacting molecules and how we can apply these formulas.